Hello, this is Jack Jackson. In this video, we're going to be talking about graphing trigonometric functions. We're going to be introducing these Cartesian graphs for the first time. Before I get started, I want to give a shout out to Janice Podorsky, who created this GeoGebra sketch that we're dealing with. Janice was one of my senior project students in mathematics, and her project was to develop applets like this for trigonometry. She based this one off of my design, but she did all the work in executing the plan and came up with a pretty good tool that I want us to look at and use in this video to introduce Cartesian graphs of trigonometric functions. So first of all, let me remind you some things about the unit circle picture for graphs for the trig functions. So here we have the unit circle, and um, the way the functions work, if you remember, the way we defined them earlier is we start with a array in standard position here with the vertex at the origin, the initial array along the positive x-axis, and we spin this thing to get a terminal array coming out this way somewhere, wherever it ends. And the path at that point 1, 0 takes along here is called the radian measure of that angle. So that arc of the unit circle is the radian measure of that angle. And then we can do the trig functions based on any point except for the vertex on this terminal ray. And we get an x and y and an r coordinate, r being the distance from the origin. And we can define the functions, for example, as sine is y over r, cosine is x over r, tangent is y over x, secant is r over x, cosecant is r over y, and cotangent is x over y. And if r is 1, then some of those simplify. For example, cosine is just the x-coordinate at this point, sine is just the y-coordinate at this point, tangent is still y over x, and so forth. So that's how we define circular trigonometric functions. If we're rotating in this way, it's positive. If we rotate this way, we call that a negative. So clockwise is negative angles. Counterclockwise would be positive. If we go around more than once, this indicates that we went around all the way once and then some extra here. And we have a slider here that can change the angle from negative 2 pi radians to, I guess, 4 pi radians. Okay, so we have something like this. This thing right here is called the reference triangle, which is a right triangle. And so in some sense, everything is still based ultimately on a right triangle set up there. But we've extended that to circular trigonometric functions. Okay, now, so we are going to switch this to trig functions of an angle. And so here what we're doing is we're transferring this picture in the unit circle over to a picture in a regular Cartesian graph. So the first thing that you need to make the connection, and this is for all the trig functions here, is that what the input is. Over here, the input is the angle, the rotational angle, the amount of rotation. That is also this arc length here on the unit circle. That is the radian measure of that angle. Now, if we just take that and straighten it straight up, or to straighten it out and lay it over here, we get a line segment of the exact same length. So this length is the same. So for example, if you go from here to here, that's 0 to pi, right? 0 to pi for the arc length. And so this goes from 0 to pi here for the straight length over here. Okay, so what is an angle over here in the unit circle picture is an x value over here. The angle being the arc length over here in the unit circle picture, and the angle being, or input being, the horizontal distance here on the, or just the x coordinate over here on the Cartesian graph. Okay, and that's the first connection all the way. The angle in radians, arc length, is the unit circle. It's the x value, distance from the y-axis, or sine difference, distance, for that. Now let's look at sine. Now let's think about this. Over here in this picture here, remember sine is just y over r. R is 1, so the y is the is the sine. So on the unit circle picture, y is the sine of the angle. But over here on this picture, we want to graph y equals sine of x. So y is the sine of x. So the y here on the right is the y here on the left. I've done these at the same scale so that 1 is 1 in this picture. 1's 1 in any direction on this picture or this picture. It's the same scale. So notice that we just bring that point straight across and put it over this x value there, and there is our point. So let's look at what happens. Let's start at, say, at 0, and look what happens as we start out at 0, 0. 0 radians input gives us a 0 y coordinate here. So that means we start at the origin over here. As we go here, increase in our first quadrant, these are going up. It maxes out at 1 when the angle is pi over 2. Then it comes back down to 0, bound into the negative. Sine is negative when the terminal side is in this third quadrant, which corresponds to links right in here. And it comes down. The lowest it gets is at -1. That happens at 3 pi over 2. And it comes back up to 0 at pi. And then we repeat the same thing over again. Okay, well, what does that chase? Can you see that thing going up and down? Okay, it's actually chasing out this graph here. And so the graph of the sine function is actually a wave. And you can see that it just keeps repeating the same pattern over again. Every time we go all the way around the circle once, over here in the unit circle picture, we're at the same position, same terminal ray. So we have the same, all the trig functions are the same as when we were there last time, if we go around the circle more than once. And so we see that we get a repeating pattern that is 2 pi long. So we say this has a period of 2 pi. So for example, this section from -2 pi to 0 is repeated again from 0 to 2 pi. And it's just repeated over and over and over again as we zoom out. You can see that. Okay, so that's sine. Well, how about cosine? So once again, sine, the input here was the angle. The input here is the x value, same value. Here, the y value is the sine of this point here on the circle of the terminal ray. And over here, the y value is the same thing. So that just comes straight across. All right, how about cosine? Well, cosine is very similar, but there's a slight difference here. Okay, so let's set theta at 0, and we see that the cosine is the x value of this point here, which is 1. So it's going to start at 0, 1 over here. Now look what happens when we move this around. So let's look at what's happening over here on the picture on the left, first of all. For cosine, when we take our terminal point here, it's its x-coordinate that is the cosine, which is a horizontal distance over here on the unit circle picture. Over here, it needs to be a vertical distance, so we just simply rotate that around pi over 2 radians, or 90 degrees, and then pull that straight across over here, and that becomes the cosine. So look what cosine does. Let's start again at 0. So it starts at 1. As we increase, the x value the x value is starting to come down over here. So it's an x value here on the left, it's a y value on the right. And so it starts coming down, it hits 0 when we get to pi over 2, and then goes into the negatives when the angle over here, terminal side, is in the second quadrant. working its way from 0 down to -1 at pi. Now, still negative here, working its way back up to 0 at 3 pi over 2, and then back positive, working its way back up to where we started at 1. And then it repeats the whole thing over again. So once again, it looks like it's maybe some kind of a wave. Let's take a look at what that traces out. Yep, sure enough, it's a wave. It looks very much like the sine wave. It's actually just that sine wave shifted over a little bit. And so we get the cosine curve there. And once again, it has period 2 pi, which makes sense because as this thing goes around the circle one time, we go through, like say, once again, as we go around the circle from 0 to pi, we trace out one cycle, and then we go around the circle again, we trace out the same thing again, and again, and again, and again, as it goes further and further out. So there is the cosine graph. So sine and cosine are wave graphs. Okay, now what about tangent? Okay, tangent's a little harder to see, but we can still do it. Tangent is y over x. Now, if we wanted to see the tangent as an actual length, then if we could let the x be 1, we could get the tangent. So here's what we end up doing here. We actually draw a tangent line to the circle right here at y or at x equals 1. And as we, let's see, let's just do a nice little first quadrant angle to get started. Look at the triangle that's formed right here. We have the little right triangle, which is our reference triangle, but we have a similar bigger right triangle here. In both cases, we can take a point on that terminal ray. In this case, we're going to go where that terminal ray hits this vertical tangent line. Could have something to do with the name of the function here. Tangent function, tangent line. And we have y over x is that tangent of that angle. Well, x is 1 here, so y is the tangent. So this distance, vertical distance from here to here, is the tangent. Well, it's a vertical distance here. We want it to be a vertical distance over here, but it's not a vertical distance in the reference triangle. It's in this larger triangle here. And notice that this works out from, again, let's start at 0. We notice that then tangent will start at 0. As we go in the first quadrant, it gets bigger and bigger and bigger. It goes way up there, right? Well, what's really interesting here is when you ever actually get to pi over 2, then your y, it doesn't hit that point. Or if you just take this point 0, 1 on the unit circle, when you do y over x, that's 1 over 0. That's undefined. So the tangent does not exist there. And what we see here on the graph is it's going up, higher and higher and higher toward infinity. We have a vertical asymptote there. Okay, what about in this quadrant? Well, if we take this ray, and not where the ray won't actually meet this line, but take the line containing the origin and that terminal point. So see where it hits down here, and we take that y value and bring it across. Again, this y over 1 will be the tangent of that angle. Notice that when you look at this reference triangle and this one here, they share the vertical angle right there. So they're going to be the same value, and we get the correct positive negative sign of it because in this quadrant, tangent is negative, and that does give us a point down here that we can bring across. And so notice that in this quadrant, we get this length, but down in the negatives. So it's down here. And then once we get to right at pi, we're back at 0. Now this quadrant, we're back at 1. So again, take that point and the origin, and that gives us a point on the terminal ray. down here, but a point on this vertical tangent line if we extend it back with the line through the origin. And that gives us positive tangent values, which are down in this quadrant. And we get here. Now, one thing we would notice then is that we get this a cycle that repeats every 2 pi, but we get a little bit of a bonus here for tangent. Here's what the graph actually looks like. And the bonus is that when we go pi, if we go from, say, 0 to pi, or let's go from minus pi over 2 to pi over 2, this little part right here traces the entire pattern one time. So tangent actually has a period of pi rather than a period of 2 pi. And the bonus is that the parts down in the third quadrant repeat the parts in the, let's see, so there are parts in the, let's see, the parts here from the fourth quadrant are repeated in the second quadrant over here. And the parts in the third quadrant are just repeating the parts that were over here in the first quadrant. In other words, this piece right here on the graph represents the first quadrant over here. This piece here represents the fourth quadrant over here. And if you shift that by pi, you get stuff in the second and third quadrants. Well, the second quadrant, which is here, is just repeats of what's in the fourth, and the fourth quadrant here is just repeating the stuff that's in the first quadrant. So you get a period of pi. And so we get some interesting things about the tangent function. Notice it has vertical tangent lines, vertical asymptotes, where it's undefined. Okay, when we look at this vertical tangent line over here, we have vertical asymptotes here, and they occur at odd multiples of pi over 2, basically at pi over 2 plus multiples of pi. And it's increasing on each piece and so forth. And we'll look more about the characteristics of all these graphs in our next video. But we can see how to go from, so we were able to take sine, cosine, and tangent from the unit circle picture and transfer them over to the Cartesian graph picture. Okay, now let's go on to secant. All right, so let's look at the picture here. Now, secant is that's the reciprocal of cosine, so it's going to be r over x. So if we could get x to be 1, then the radius then would be the secant. Okay, so once again, we're going to use the same tangent line that we use for tangent, and we're going to use the same triangle. So the tangent, remember, was the distance from this point at 1, 0 up to where that terminal ray met that tangent line. It was the y value here. That y over 1 would be the tangent of that angle. For secant, it's the hypotenuse over adjacent, right? Adjacent is 1. So hypotenuse, r, divided by x. X is 1, so it's just r. So this brown length from the origin out to here is the secant. Now we want to rotate it up. So I rotated it up vertical and then brought that across, and that gives you the secant value over here. So let's start it at 0. So we start at 0, we see the secant is 1, so it starts here. And as we go across here, it's going to get bigger and bigger. And it gets really, really big, so that as you're approaching pi over 2, it is approaching infinity. It's going way up there. So basically, again, it's undefined when at x equals pi over 2. And just like the tangent, it's going to have a vertical asymptote there. Well, what happens when you get to the second quadrant? Just like with the tangent, we're going to bring that point on the terminal ray right there through a line through the origin and see where it meets this vertical tangent line here. And once again, our tangent was the y value on this vertical distance. The secant is the length of that hypotenuse, the r value there. Well, we in this quadrant here, secant is 1 over x. X is negative. See the actual points over here. So we need the y to be negative here. So we want to rotate this hypotenuse down vertically so that we get a y value that is negative for the secant there. So then this quadrant here, second quadrant, we get negative values of secant, which is below the x-axis over here in our wave graph, well, it's not a wave, but in our Cartesian graph. Okay. What about in this quadrant, third quadrant, we're back to positive values. Let's see, let's see, where am I here? We're still at negative values here. So when we take this point, we have to rotate it around to the negatives and bring it across. And then when we get in the third quadrant, we have positives, so we have to rotate this amount up to the positive part and bring it across. So it's a little more complicated, but it still is we can do that. And so when the dust settles, here's what we end up with. So again, let's start at 0. We're right here at 1. Okay, so again, if we just take the point on the unit circle, r is 1, x is 1, 1 over 1 is 1, secant is 1, secant of 0 is 1. Okay, what happens is we go in the first quadrant here, it goes up from 1, it gets longer and longer and longer, approaching infinity, undefined at pi over 2. When you go to the right of pi over 2, we're in quadrant 2, which is over, between here and here for the unit circle picture, between minus pi over 2 and pi in the Cartesian picture. And notice we have negative values down there. They start infinitely, very, very, very far down there, coming from negative infinity up. And then eventually they get up to and stop and turn around when when y is negative 1, which happens when x is pi. So of course on the picture that's when you get, I can just put in pi right here, then we're at negative 1 there. And then as we go a little further into the third quadrant, comes back down here. And as we might suspect, we get a period of 2 pi again. So as we go from, say, minus pi over 2 to pi over 2, that gets half of it, this upper half. And then from pi over 2 to 3 pi over 2 gets the other half, which is down here. And it just repeats that pattern over and over and over and over and over again. So you have these connected pieces, and then they have disconnects at every odd multiple of pi over 2, pi over 2 plus n pi, where n's an integer, and that gives you your vertical asymptotes. Notice that the range goes from 1 up and from negative 1 down, but there's this blank spot between 1 and negative 1 for the y values. All right, that's secant. How about cosecant? How can we see that? All right, well, let's think about our unit circle picture again. And what's our definition of cosecant? Okay, remember, it's not just the unit circle. It could be any circle centered at the origin, because you can take any point on that terminal ray except for the one at the origin, find its x, y, and r coordinates, and use those to find cosecant of the angle theta. Remember, once again, the angle theta is the arc length right here in radians, which is the x value over here on the Cartesian graph. That's true for all of these graphs. Okay, so let's think about cosecant. Cosecant's the reciprocal of sine, so it's going to be r over y. So we need the y to be 1. So notice what I've got here is this is the line y equals 1 right there. So that means this distance is 1. And if we do that, then the radius is the cosecant. So like the secant, we want to get the radius on the triangle this time. This time we just go out, we go up a distance 1, take this line right straight across, find where it crosses the ray that comes out this way at the terminal ray, and that point right there, we can use its x, y, and r coordinates to find the cosecant of that angle. Y is 1, so r over 1 is the cosecant, which is just this distance. All right, in this quadrant, this is positive, so I want that to be a y value over here. I need this length here to be the same as this. So what I did here in the picture is just rotate it up and bring it straight across to here, and we see that is the cosecant of that angle. Okay, so let's see where that's going to take us. What happens if we get 0? Well, let's think about this a minute. Let's just take this point 1, 0, and r is 1. That's 1 over 0. Oh, that's undefined. So cosecant's actually going to start undefined, and then it's actually really big in the first quadrant here, working its way down to what? So it starts really big, so it circles way out there, and then it comes down, 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 down to 1, and that happens when the angle is pi over 2. And then it starts back up when you're in this quadrant here, second quadrant. So if you're looking at the picture on the right, you start high, come down to 1, back up. You get an idea what that might look like? Well, let me just go ahead and show you. Yeah, it's a lot like the secant. Maybe you figure that out. If sine and cosine are kind of shifts of each other, you might expect secant and cosecant to be shifts of each other as well, and they are. So again, we can see what's happening here from this quadrant coming down this way and then back up. What about if you're down here in this below the x-axis, y is negative, so we need to rotate our hypotenuse down this time to get a y value that is negative over here. So we make sure we get a negative value for that. And you can see that tracing out there as well. So once again, we get a pattern that from 0 to 2 pi traces it once, and then then you just shift that over by another 2 pi, another 2 pi, another 2 pi. And so you get that same pattern going over and over and over and over and over again. That is the cosecant graph. Just like the secant graph, there's a part that's connected here that's concave up that has a minimum of y value of 1, and a part that's concave down that has a maximum y value of -1. There are no y values between -1 and 1 on the graph. Also, it has vertical asymptotes. These happen at integer multiples of pi, at 0, pi, 2 pi, 3 pi, pi, -2 pi, and so forth. And again, we'll investigate all the features of the graphs a little bit more in our next video and with another GeoGebra activity. But right now we need to see how the circle graph, the circle representation, which is our definitions of the trig functions, comes over to our Cartesian graphs. We just got one more to do, cotangent. Okay, so let's look at cotangent. All right, first of all, we need to think about what cotangent means. Cotangent is reciprocal of tangent. It's going to be x over y. And again, that's for any point on that terminal ray besides the one at the origin. And so since it's x over y, we need a y of 1, and then the x will be the cotangent. So what we do is we take this line at y equals 1. That will make this vertical distance equal to 1. And now the x value here is the value of the cotangent. Of course, in the first quadrant like this, all the trig functions are positive. So we need to take this horizontal distance here, rotate it up vertically, and bring it straight across here to be the y value here. Okay. Now, well, what happens when you're at 0? Let's just start there. Well, let's take this point here. It's the point 1, 0. R is also 1. So cotangent is well, we don't actually need r, we need y and x, right? We need x over y, 1 over 0. Oops, that's undefined. So there is no point on the y-axis here. The y-axis will be a vertical asymptote. One thing that we notice on the graphs over here, the sine and cosine wave are defined for all reals, but the tangent and the secant both had vertical asymptotes at odd multiples of pi over 2. So when they were undefined, that is when what? When the over here in the picture, when the line is pointing straight up or straight down, that's when it's undefined, and that's going to give us vertical tangent lines. Similarly, I'll go ahead and show you cotangent. There's cotangent and cosecant. They're undefined when on the unit circle picture, when let's see, cotangent is x over y, cosecant is 1 over y. They're undefined when y is negative in this picture on the unit circle. Y is 0 at an angle of 0, and also at an angle of pi, and in other things that have the same terminal sides. So that turns out to be multiples of pi, and that's where we get vertical tangent lines for both. I keep saying tangent, I mean asymptotes, vertical asymptotes there. All right, so here's what the cotangent ends up looking like. All right, so how do we see it in the picture here on the left, and how do we bring it across? Again, we take our terminal ray, go out where we have a y value of 1, where it meets that horizontal line, and the x value here, or at least that length, will be the absolute value of the cotangent. When you're in this quadrant, cotangent is positive, so we rotate that up and bring it across. When we go over into, let's see, when we get to pi over 2, let's type it in, pi over 2, it's going straight up, that's a right angle, 90 degrees, pi over 2 radians. Then we have 0 for the cotangent, so that's where the x-intercept is right there. And then as we go into the second quadrant, cotangent is negative. So this time, again, it's the x value on this graph where the y value is 1. You're on the terminal ray. That's that point. It's its x value. And so we take that. It's negative, though. So we rotate this length down into the negatives and bring it across for this vertical length right here. Okay? When you are in the, of course, when you reach pi, it's undefined. That's our vertical asymptote. When we're in the third quadrant, again, we can we can actually take this straight back across here to this line y equals 1. These have the same reference angle. So this will be, the x will down here, from here to here, will be the cotangent, because the x over the y is the cotangent, which is x over 1. And so, but over here it's an x, over here it's a y though, right? So see how that works? X over here is y over here. So we rotate it up. Again, it's not x on the unit circle picture, but x on this picture right here. And so we can see there, we get that, and it goes around here. So we're down into the negatives in the third quadrant. And as you go around, it just keeps tracing the same pattern over and over again. Like tangent, we get a bonus here, a bonus repeat. Okay, we know that if we go 2 pi over, say from here over to here, we're going to get the same value, y value. That's because we're, at the same terminal side. But for tangent and cotangent, we get a bonus, because if you rotate it exactly halfway on the other side, then you also get the same y values as well. Okay, so a extra pi rotation over here doesn't leave you at the same terminal side. It leaves you at the opposite terminal ray, but the opposite rays always have the same tangent and cotangent. So here we shift to the right by pi. We're at the same right another pi, or shift left by pi. And so we see the period is pi. So if we just go from 0 to pi, this piece right here gets the entire pattern, and you just repeat it over and over and over again as we shift further and further to the left or to the right by multiples of pi. Vertical asymptotes are at multiples of pi, at 0, pi, 2 pi, 3 pi, negative 2 pi, and so forth. So now we have seen how we can take the unit circle picture and get our pictures of our trig functions. There's sine, cosine, shifts. Here's tangent. Here's cotangent, not shifts. Notice the tangent is increasing on each piece, cotangent is decreasing on each piece. There's an interesting relationship between sine and cosecant. They are reciprocals of each other. Notice that they touch each other here. When sine has a maximum, cosecant has a minimum, and vice versa. Sine fills in the part between 0 and 1. Secant or cosecant's outside of that, from 1 up and from -1 down. They both have 1 and -1 for y. A similar relationship between cosine and secant. So sine and cosine are just shifted apart by pi over 2. Secant and cosecant are just shifted apart by pi over 2. Tangent and cotangent, not shifted. It's actually a reflection with a shift. Okay, so that gives us a nice introduction to how to take the definitions of the trig functions, which were based on a unit circle picture, and from that get the wave graph for a sine or cosine, or general Cartesian graphs for the sine, cosine, tangent, secant, cosecant, and cotangent. In the next video, we'll come back and talk about the properties of all these graphs in a little bit more detail.